Welcome guys to another session in Paths and Graphs DPV 4.6, and today we are proving Dijkstra's shortest path tree is actually a tree. Um, so with that introduction, let's dive in. So before we try to understand the tree structure of the Dijkstra's algorithm, let's just quickly look at this problem here. So it's a problem where we have a start node and a bunch of nodes that are connected to the start node. And the way Dijkstra's algorithm works is that you start here and then from here you try to find the shortest path, right? So you might find the shortest path here coming out of S1 is this 25 here to 7. And then from there you can try to find other paths and so on. And so every time you find a node that's connected to the start node through some other networks, once you find the shortest path to a node, it is relaxed, which means that it no longer is in the nodes that are uh, being reached through the shortest path Dijkstra algorithm. So this relaxation algorithm means that every node that is found to have the shortest distance from S1 in the set um, then has just one parent, and this parent pointer is pointing towards that parent. And as soon as you discover this pointer, it is removed from the nodes where you compute another shortest path for this node. That is the way Dijkstra's algorithm works, and that's why it does not work with negative values, because you never again would look at once it's relaxed, it's relaxed. So that's the important part of the Dijkstra's algorithm that I wanted to point out here. Now, once you run through this, some sort of a tree, some sort of structure emerges. Let's not assume it's a tree, but some sort of a structure emerges, and every node, let's say, points to one parent node, and eventually you find from any node you can trace a path back to the start node. And if you look at the distance, in this case, the least distance is found to every single node, assuming all these weights are positive. You find, like 50 and 26, if you add them up, that is the distance, shortest distance to this node. And then 25 is the shortest here. And then for 3, it'll be 50 plus 10 and so on, right? Now, so the observations that we have is that this tree is fully connected. Dijkstra's algorithm does find the shortest distance to every node. So there is a path that connects in this output tree to every single node. And there is only one parent, right? And that's based on the observation that there is this relaxation algorithm that removes you from the search once the shortest distance to that node is found. So we have one parent and we're fully connected. These two things are our assumption now. And now, so we have to prove that there are no loops. And once we prove that it's a fully connected graph and there are no loops, we can claim that it's a tree, right? So how do we prove that there are no loops? Well, in our example, we don't see a loop. So the way I would approach this is, let's just say in this example, there was an edge like this. And it would form a loop on these nodes, right? It's not all the nodes, but at least if you look at it, there is the shortest path here to 4, and the shortest path to 4 was kind of like this. But let's say there was a shortest path to 4, which was yet another path. Um, and I'm sorry, shortest path to 2, that was yet another path here. So how do we prove that this cannot exist in a Dijkstra tree, right? The way to think through this problem is that I'm going to assume two things. One, that the start node is within this loop, and the other is the start node is outside this loop. So you need still a path within this loop. You don't have a start node, which means that there is a path that leads from here up to the start node. Imagine start node is up on the top of a mountain, and this is some nodes in the valley or something. You still need a path up to the top of the mountain where your start node is, right? So you still need a path there, which means that you need a bunch of links to the some other set of nodes, which will eventually lead you up to the start node. So So let's take the first case. If the start node is inside this loop, right? If you're inside this loop, let's say 4 is the start node, it cannot happen because um, as you can see, 4 has 5 as its parent. And so start node by definition cannot have a parent. So this start node cannot be inside this loop. That would be a contradiction. If the start node is outside this loop, then also imagine the other problem, which is that there must be some node that then connects you towards the start node. Let's say these nodes are not, there's no start node here, but you must have a path up, parent, 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 and eventually leading up to a start node. And that's how you would have arrived to one of these nodes. Can't be, I mean, it doesn't have to be two, could be one of these nodes. And now if you consider that node which has a path to the start node, there must be up, up, up to the parent till you reach the start node. Now, what's the contradiction there? If you look at 2, since it's part of this loop, it has this arrow to its parent here. And then it also must have another parent because there's the path to reach the start node. So 2 would have two parents, one that is pointing towards the start node and one you already know there's a loop here. So if you can find a loop inside Dijkstra's tree, you can prove that that would be a contradiction, right? And there is no way you can have a loop. Now, another way to do this would be, let's say 2 was a distance 50 from the start, right? And so if you go down this loop, let's say this distance, loop distance was 10. So this was 50 from the start, 50 minus 10, the parent would be at 40, and then minus 10, this would be at 30, and then this actually became negative here. So it does not even make sense. But let's say if you continue down this path, and this was like, much larger number, once you go down this path and you come back to 2, now the distance, now if you went down this path, the distance to 2 is smaller, right? And so the distance to 2 keeps getting smaller as you go down this loop. And so the loop cannot exist because then there must be another path that can give you a smaller distance from the start, right? So, um, so by that um, contradiction, the fact that you cannot be in a loop because every time you go around the loop, your distance keeps decreasing, and because you're pointing towards your parent, so on and so on. So every time you go around this loop, your distance keeps decreasing and your shortest distance just keeps decreasing, which does not make any sense. So by these methods, you can prove that there is a contradiction either way. Um, and if a loop exists in Dijkstra's tree, it would always lead to a contradiction. So we can assume that there is no loop in Dijkstra's tree, Dijkstra's graph, and therefore it's a fully connected graph which does not have a loop, therefore it must be a tree. So that's the solution to this problem. If you guys have any confusion or if you do not agree with the solution, leave me some comments. I have thought through the problem for quite a while, and I think it makes sense to me. And I've tried to prove it two ways that a contradiction is going to happen if you proceed down this path and assume that it is anything but a tree. Now, I also wanted to say that a couple of words on what is Dijkstra's tree and how does it relate to Prim's, let's say, minimum spanning tree, right? So if you want to think about spanning trees, think about a problem like you're constructing a city and you have different points in the city, you want to connect them and you want to use the minimum material to build the roads, right? That would be the problem of the minimum spanning tree, that you want to build a city with the roads. Now, Dijkstra's problem is that let's say the city is built. And if the city is already built and you're being asked, hey, what is the shortest path of taking you from node A to node B or node S1 to node 4? That is the problem that Dijkstra's algorithm tries to solve for. And obviously Dijkstra doesn't take into account negative weights, et cetera, et cetera. But that's the difference between, if you look at it, that's the difference between a Dijkstra tree and the Prim's minimum spanning tree. Dijkstra is not trying to find or optimize the cost of the whole layout, right? What is the smallest cost to build a network Dijkstra is not trying to do that. It's just trying to find the shortest um, single source, shortest path to all the nodes in the graph. And that turns out also to be a tree. So thanks for watching this episode, guys. Hopefully you liked it. And if you did, give me a thumbs up. That keeps me motivated to bring you more solutions in the same episode. And so if you subscribe, I would also appreciate that. That tells me that you are enjoying the videos that I'm making. So with that, I'll wrap up this video and I'll see you in another video. Thanks a lot and bye-bye.